Hello students, now we are going to discuss a major concept of mechanics which is going to help you not only in this chapter but many chapters to follow. A good understanding of this is going to help you in the next year course and your understanding of physics as a whole. Now in this chapter, basically we'll be seeing what is the effect of forces on the bodies, and the bodies what we are going to talk is the normal size bodies. Not we are not going into the subatomic world and the atomic world. So it is on a much bigger scale. The laws was proposed by Newton for such bodies only, and even bigger bodies, celestial bodies. So before we go on to the effect of forces, let us just understand what forces are there. Even though all the forces won't be required, what we are going to deal with majorly is the gravitational force and the contact forces. But then fundamental physics tells us which forces are existent. Then those are your, as I said, gravitational force, then so let me write gravitational force first. Then the one which knowing or unknowingly you are always under the effect of, as you are under the effect of gravitational force all the time, this is electromagnetic force. And the ones which we know very less about are the weak nuclear forces and the strong forces. So these are the four fundamental types of forces what physicists deal with, and they are trying to unify all of them. They have proposed a name for these two unified, electromagnetic force and weak nuclear force, as electroweak force. But thankfully we don't have to go into the subatomic level and understand what is happening. Meaning to say, if I've got a body of some mass m and I'm pushing with force F, then what we are going to study is what is the acceleration of the center of mass of the body or the whole body as one. What is the acceleration of the body? So that would be given by Newton's law, F is equal to m, and we'll see how to apply what all forces we have to count over here, and this acceleration means the acceleration of which part. But we are hardly concerned about how the masses internally in this body were attached to each other. So these masses or the molecules inside the body, they have got electromagnetic forces between them, but we are not bothered. Meaning to say, coming on a bigger scale, if this was a 2 kg body and you had glued a 1 kg body with a 1 kg body, if you have glued a 1 kg body with a 1 kg body, or you had nailed a 1 kg body with a 1 kg body with the negligible weight of the nails, it doesn't matter. Ultimately it's a 2 kg body and you have the same force applied, then whether they were glued or nailed, they would be going with a given acceleration. So it doesn't matter that internally what is happening in the body, internally what are the attachment forces. So on a microscopic level we are going to ignore, we are not going to go into that. Thankfully those forces, we are not going to ignore them. Those forces are existent, but those forces are not going to make a difference to what we are going to study. So what we are going to study is, gravitational force would be acting on all the bodies what we are going to study, because we are going to do most of the questions which are dealing with bodies which are near to the surface of the earth. So earth is always pulling them. This is your earth, and earth is always pulling the body down with a force of mg. So in your gravitation chapter, we are going to understand what is the value of the g more clearly. Means the formula g mm by r square, where r is the distance between the center of the earth and the body in question. So that much will be the force with which the earth will be pulling. So that will be existent all the time, and then we would be pushing or pulling the body, and our force will count as contact forces. The other contact forces will be air resistance would be there. There would be resistance from the ground, which will be friction, and from the other blocks. So various contact forces would be there. And it is very interesting to know that all those contact forces are actually electromagnetic force. So one fact I find very interesting, and I always discuss with the kids, I love to discuss because it fascinated me so much when I came to know about it, is that even when I'm pressing this say red block onto the blue block and I'm pressing it very hard, if you can see, then is any part of this actually touching this? If any, is any part of the red block touching the blue block? To tell you the truth, it is not. The molecules or the atoms, if I go to the subatomic level and the atomic level in fact, then the atoms are far, far away. Say these are the atoms of the red block. Then what I have managed is the blue block, maybe if I have pressed very hard, somewhere over there. No way have I even got the nucleus of this come to as much as a distance, how much ever the nucleus of the red block itself were apart from each other. My blue block has not even gone to that level. If they are fused, maybe to that much of distance. So this distance, the interatomic distance of the red block, may become that on fusing and all, but on pressing and all, it is way far away, and it is almost impossible to get this nucleus on that. That is what happens in nuclear fusion. So we are obviously unable to do a fusion over here. Why it stops and what makes us feel that it has touched something is because the electromagnetic forces starts acting, and this red one starts repelling this blue one. They start repelling each other, in fact. They start repelling each other because of the field, the electromagnetic field they are having, and the electromagnetic fields will repel each other and it will feel as if you have touched something. You can imagine like your nails were strong magnets of say North Pole, and this nail is also strong magnets of your North Pole again, and you close your eyes and you bring them together. Your hand is ultimately going to stop. Your fingers are ultimately going to stop. For others, it may seem like, why are we not bringing the fingers together? There's a lot of gap. If a mosquito wants to fly through it can fly through it. But there is lot of forces between, and we are not able to overcome the force. So that is what is happening even when you feel it has touched. So nothing has touched. All distortions may be happening, but nothing has touched anything. So they are in fact all non-contact forces. So the term contact forces is basically for the electromagnetic non-contact force. In most of the cases we know, like friction, air resistance, and whatever. But anyways, we don't have to bother about all these. What we have to bother about a non-contact force of gravitation, and all other forces of these kind, what we are saying, it will come under contact forces. So the forces what we are going to have as contact forces will be tension, normal reaction, then you will have tension from spring, you'll have friction. So there will be several forces which will be under the contact forces. So microscopically it will be all non-contact forces. So anyways, we don't have to bother about it. So like particularly this tension, what happens when you are pulling, say there is a steel wire and that has been pulled from both ends. So what is happening? The molecules are trying to go away, but then the molecules are at a certain distance from each other. If you try to push them in, they repel as if they were attached with a spring. If you push them in, they will repel. They will not try to come in. It is very difficult to compress liquids and solids particularly. And if you pull them, they are again trying to pull themselves back in. So it is very difficult to stretch them also. But they can get stretched, but they will pull it in. It will behave like a spring. So that again will be dealing in properties of matter later on. So here basically what I was saying earlier is this thing. You have a block, you have a mass, you have several masses, and those are experiencing some forces from all around, and they are always experiencing one extra additional force, which is your pull from Mother Earth. So that is your gravitational force, and the net force on the body is going to result in some acceleration of the body, and that will be governed by Newton's law. And the Newton's law work very well on these massive objects. We are able to make very precision instruments and machines, cars and everything very, very precisely using Newton's law. So it is not that it fails. The classical physics laws works very well on massive objects. It is only that when we go to a small level, then all quantum physics starts coming into play and things get really weird. So weirdness of all these weak forces and all is beyond the scope of our curriculum for JEE. So before I go on to discuss the laws of motion and its effect, let me just talk a bit about tension force and normal reaction, and maybe a bit on friction. So this is what we'll be dealing mostly with in the initial problems, and later on we'll introduce friction and spring. So what is tension force? By the way, if we talk about the effects of those forces which I listed on a very small distances as small as the diameter of a nucleus and all, then gravitational force is one of the weakest force. It is one of the weakest force among all the forces. It is in the order of 10 power minus 30s if I start measuring the strong forces and all, and your electromagnetic force itself will be 100 times smaller than the strong forces. So but as the nucleus becomes bigger and bigger, then the strong forces, the force between this particle and this particle, the interaction of strong forces becomes less, and the electromagnetic force becomes more prominent, and the nuclear is more probable to rip off. And when we are talking of these forces, and the weak force will be in the order of 10 power 10 or something, your gravitational force is way less. Maybe 35, maybe 38, very less compared to all these forces. So a gravitational force is, to give you an example of how small it is compared to magnet, just imagine this being your Earth and that being your Mount Everest. Yes, your Mount Everest will be even smaller than what I have made over here compared to the radius, in the comparative radius. And then just imagine how big a building will look like in front of Mount Everest. So it is that small, and the whole Earth, the whole mighty Earth is trying to attract this cow from Switzerland towards itself. And when I leave it, it is able to attract it. It is going down, and it is a force of mass of this cow into gravitational field strength over here, which is around 9.8 meter per second square. That much of force is acting on the cow and is going down. And to counter that massive earth, if I have just a small piece of magnetic material, then you see what happens. This magnetic strength overpowers the whole mighty earth. This small piece of magnetic material, this iron, and the magnets are down in the belly of the cow, is able to counter the force of earth very easily. That is, the whole of earth is not able to pull this with the strength with which this rod is able to pull the cow up. So just imagine how weak is your gravitational forces. Even though it is very weak, that's the force what we are going to deal with mostly. And the electromagnetic force is what is keeping our bodies together. If the whole building has to crumble and all the electromagnetic forces go away, then it will not be even a speck of dirt if everything has to come together. So it is two nuclei are not coming together because of electromagnetic repulsion between them. If that goes away and everything is together, then they say that the whole of Earth would not be bigger than one small cricket ball. So that was just to give you a perspective of gravitational force in front of the other forces. So the binding of our body is not by gravitational force. The binding of our body is by other forces. What were listed? Mainly electromagnetic force. But then the external force, what is acting on the body. So that is what we are going to study.